Dynamic programming. So finally, we are here at the most interesting and the most challenging topic of programming interviews. And what is dynamic about dynamic programming? Well, actually, there is nothing dynamic about it. Interestingly, somebody just came up with this name just because it looks cool, and this doesn't really have a meaning to it. So you can just take dynamic programming just as the name for this approach. All right. So before we go deep into dynamic programming, let us quickly revisit our fib series. So as we saw in the recursion video, if we would say like to calculate fib of 5, the recursive approach takes us to first to fib of 4 and then to fib of 3, and fib of 3 goes to fib of 2 and fib of 1, and then once that returns we have fib of 3, and then the stack returns back to fib of 4, and once we have fib of 4, then we calculate fib of 3. But note that we had already calculated fib of 3 here. We are just, when the stack got back from fib of 4, we are just ending up recalculating fib of 3 to do the fib of n minus 2. So we recalculate fib of 3, and ultimately we have the value for fib of 5, which is fib of 4 plus fib of 3. So can we do better? Can we improve our complexity by not recalculating numbers that we had already calculated before? So here is the recursion tree for fib of 6. Here in the figure on the top is our regular fib series where f of 6 leads to f of 4 and f of 5 and so on. So here we had calculated f of 4, and here again for f of 5 we have the same tree being calculated again. And this approach of every node having two children is what gave us our 2 to the power of n complexity. So if we were, however, to cache the values that we have seen before, our complexity goes down a lot, a humongous lot. So on the figure below, you can see that f of 6 leads to f of 4, and f of 4 would lead to f of 2, then we get f of 0, we return back up, we again do f of 1, we back up, and once we have f of 2, since fib is n minus 2 plus n minus 1, we try to calculate f of 3, and this leads to f of 1. This is a base case, so there's nothing much to do about it. It gets back. And now when we try to calculate f of 2, instead of again calculating f of 0 and f of 1, we just reuse the value that we calculated here. So when we try to calculate f of 2, we reuse this value here, right? And the tree goes back up, so now we have the value for f of 4 here on this edge. And to calculate f of 6, we need f of 5, which in turn needs f of 3. But this entire f of 3 had been calculated here. So we have this value here. So we can instantly go back up and try to calculate f of n minus 2 for f of 5, which is, sorry, n minus 1, which is f of 4. And this, but f of 4 again had already been calculated here. So again, we can instantly reuse this value instead of going through this entire subtree. So as you can see, except for a few numbers here at the lower end, most numbers are just being calculated just once. So this brings down the complexity to O of n, while this one was O of 2 to the power of n. So this is almost a linear tree, because for example, if we had f of, say, f of 7, this would just be f of 7, and this will be f of 6 and f of 5. But again, since we had already calculated 5, this would just be, a reuse of the f of 5. So you can kind of see how every number is just leads to, a constant number of operations, and for n numbers we have n calls leading to an O of n, or a linear time complexity. Alright, so just a quick look at the code. So the basic idea is that we have a cache here, and the idea here is that we know that the fib series, there is no 0 after the first number in the fib series. All other numbers are non-zero. So if our cache has a 0 value for a particular number, it obviously means that we haven't yet looked up that number. So if, say, we are looking for a particular number and the value is 0, so it means we haven't looked it up. So we not only calculate it using the usual formula, but we also store it for future reference. And say the number were not 0, we get here to the else part. If the number were not 0, it means we had seen it previously and we have it stored here in our cache. So instead of going with the n-1 plus n-2 formula, we just return it from our cache. So, and ultimately, to print the series, you just have to go through your cache. So this leads your overall time complexity to be O of n, and also your space complexity to be O of n. So another example, moving on from the fib series. So in this question, let us say you would like to compute the shortest path from node A to node F. The numbers by these arrows represent the edge cost. For example, so the numbers by these arrows represent the edge cost. So for example, if you would like to go from A to D through this route, the cost would be 2 plus, again, if you'd like to go from B to D, the cost should be 1 plus, and from D to F, the cost should be 15, giving a total cost of 53. I mean, clearly this is not the cheapest way to travel, because you can, one obvious way is go from D to E and then go from E to F with the cost of 2 plus 10 plus 2, which would be 14. So the question is now, how would you calculate the shortest path from node A to node F? And to make the question more interesting, you can also assume that some edges may have a negative number instead of just a positive cost. Some cost can be negative, and your aim is still to find the cheapest way to travel from node A to node F. Okay, so the most obvious way to calculate the cheapest path is that you obviously have to traverse every path, especially if you would have some negative costs. So say you can first go from A to B, and then from A to D, and then D to F. So this would lead you to a cost of 53. However, and then after getting to F, you realize maybe, you could have tried a different path. Obviously, this is not necessarily the cheapest path. So you backtrack to D, but you don't have any other way to go from D. So you just got to backtrack to B. But when you get to B, you realize B to D was not the only path. So maybe you could have as well gone from B to E. So now you try this path, and from E to F there's just one path, so you just got to go that way. And this leads to a total cost of 14. But then you again realize, well, this is not the only path, so you again back up. There's no other path. You back up to B, but you have visited both the possible paths from B, which is B to D and B to E. So there's nothing else you can do. And so you back up to A. Right? But once you get to A, you realize A to B wasn't the only path, but you could also go from A to C. And by the way, this is clearly depth first search on the entire graph, because you just take one path and you follow that path all the way till the end, and then you backtrack. Right? So now we are done with A to B, and now you would like to try A to C path. So you go from A to C, and say you could go from C to D, and then D to F. And this leads to a total cost of 55. But then again, you backtrack. There's nothing else from D, so you backtrack. But then there's an interesting path from C, that is C to E. That's still an unexplored path, so your depth first traversal continues. So you take the C to E path, and then you go from E to F. So this leads to a total cost of 6. And then you back up from F, and then you back up to C. There's nothing else to do. So you go back to A, and you realize you have traversed all the paths. So your total cost, your total, these are all your total, or sorry, these are all your different costs, and 6 was the cheapest that you could find. Right? So 6 was cheapest because you go like this, leading to a total cost of 6. Sorry. So talking of the time complexity for this approach, so let us say there are k nodes here, and there are k nodes here. So this would lead to a total of k by k edges. So if there are this is 1 hop, this is 2 hop, and if there are n such hops, our total time complexity would be k into up to n times, since we are literally traversing every path. That's clearly not a very desirable time complexity. So let us see how the concept of caching can help us, or how the concept of storing the values that we have calculated before can help us. And this is essentially the dynamic programming technique. So let us start from the right hand end. Clearly the cost to go from F to F is obviously 0, so we already have it here. Next, the cost to go from D to F, there's obviously just one path. So the cost to go from D to F is 50. Again, the cost to go from E to F, there is just one node, or sorry, one path to go from E to F. So clearly the cheapest way to go from E to F is 2. So now if I would like to calculate the cheapest way to go from, so if I would like to calculate the cheapest way to go from B to F, all right? So one way is to go from B to D and D to F, and the other way is to go from B to E and E to F. But interestingly, since we know the cost from D to F, I don't really need to recalculate what would be the cost from D to F. I just know that the cost from B to D is 1 plus whatever is the best way to get from D to F, right? If I had to go to F from B to D and D to F, I don't really need to worry about how would I get from D to F, because that the best possible cost is already stored here. So the cost would just be, the cost of getting from B to D and whatever is the best way to go from D to F. Likewise, if I would like to go to F from B to E and E to F, I already know that the best way to go from E to F is 2. So the cost of going from B to F by going from B to E and E to F is 10 plus whatever is the best way to go from E to F, which is 2. So the best way or the best cost to go from B to F is 1 plus the best way to go from D to F, or 10 plus the best way to go from E to F. And obviously 12 is cheaper than 50. So irrespective of how you would get to B, we know for a fact that the best cost from B to F is 12. Likewise, to go from C to F, one way is C to D and D to F, and the other is C to E and E to F. So the best cost would be 2 plus 50, or 1, which is the cost from C to E, and 2, which is the best cost from E to F. So clearly the best cost from C to F is 1 plus 2. So now we know for a fact that the best cost from B to F is 12 and the best cost from C to F is 3, irrespective of how you would get to B or C. So now if you would like to calculate the best cost from A to F, well, you could get from A to B in 2, and from B to F, I don't really need to worry how. I know for a fact that the cost from B to F is 12. The best cost from B to F is 12. So unlike last time, I'm not gonna again try or worry about if it is B to D or B to E. I just know it for a fact that the best cost is 12. So instead of recalculating it, I know that if I were to go the B route, the cost is 2 plus whatever is the best cost here, which is 12. Or if I take this route, again, the cost to go to C is 3, but again, I don't worry about how I would go from C to F, because I already know it for a fact that I have already stored it here that the best cost from C is 3. So the best cost from A to F is the minimum of going from 2 plus 12 or 3 plus 3, and clearly the best cost from A to F is 6. And talking of time complexity, clearly we are just visiting each edge once. So this leads to a linear time complexity. So here, when we started here, we visited this edge, and we had the minimum cost from here. And then here again, we just visited each edge and found the minimum cost for these nodes. So clearly, the cost is linear, or more formally, the cost is V plus E for vertices plus edges. Okay. So let us look at another interesting question. Let us say a thief has entered your house, and obviously he would like to steal the most valuable items. But however, he can't steal the entire house, so he is limited in the number of items that he can steal. But obviously the thief would prefer to steal the most valuable items instead of stealing the least valuable items. Here in this table, you have the weight of the item and the value of the item. And let us say that the thief is a single person, so he's constrained by the amount of the total weight that he can steal. So clearly, the most valuable item here is the last one because it is twice as valuable as its weight. So the most intuitive approach would be to steal the items that would give you the maximum value for its weight. Clearly, the last one is giving you $2 per LB. So if you are constrained by weight, if weight is your limiting factor, the most intuitive approach is to sort the items in terms of the value by weight ratio and pick the items that give you the most value per LB, per unit weight. So clearly, this gives you the best value weight ratio followed by this and then followed by this. So the ranking would be 1, 2, 3. So clearly, the intuitive approach would be to go with the one that gives you the most value for the weight, which would be the first option would be 4 and 8, and then the second one, and then if you're done with, if you're done stealing 1 and 2, and if you can still carry more weight, the next option would be the third item. While this approach is the most intuitive approach, does this necessarily give you the maximum value of stolen items? So let us see if the thief can steal a maximum of 20 LBs, what could be his maximum value of stolen items? Clearly, if he can steal 20, he cannot steal all of them because the total weight adds up to 18 plus 4, 22. So clearly he can steal all of them. So his best, so the best or the maximum value that he could steal would be $18 by stealing the first one and the third one. So his total stolen items would be 14 LBs, while the value would be 10 plus 8, 18. So although his maximum capacity is 20, he just can't steal more than 14 LB because if he picks the next item, it's 8 LBs and that would make it 22 LBs, and that is beyond what he can lift. And In the first case, probably the greedy approach worked because he would first steal the item that gives you the most value to weight ratio, and that is 4, and he still has about 16 lbs left, so he steals the next one, and 4 plus 10, and now it's 14 lbs, and now he only has 6 lbs left and he doesn't have an item for 6 lbs, so he just ignores this, and he got a profit of $18. Again, what if the maximum weight that the thief could steal were just 5 lbs? Well, clearly this was 18 again. So clearly there's just one item that is less than 5 lbs. So he could get a maximum profit of $8. The interesting question is, what if the thief could carry a maximum weight of 10 lbs? Well, again, per our ranking, this one was the most valuable in terms of the value to weight ratio, this one was the next most valuable, and this was the least. Because he could steal up to 10 lbs, if he were to go with the first one, he would have picked the first one, which is 4 lbs, and he will just have 6 more lbs left. In which case, neither of these two, the first two items, are less than 6 lbs, so his maximum gain would just be $8. However, instead of going with the more intuitive approach of choosing the item with the maximum value for weight ratio, if the thief were just to go with the first item on the list, or the second item in terms of the value to weight ratio, this one here, he would exactly have 10 lb of stolen goods, which is within his maximum capacity, and his maximum profit would be $10. So clearly, going with the maximum item or trying to maximize the value by weight ratio does not always lead to the optimal value. Before we take a look at how to solve this problem, let us see how and when to use dynamic programming. So our first exposure to dynamic programming was through the FIB series, where we saw that the recursive approach leads to the same subproblems being solved again and again. So obviously, if you ever use recursion to solve a question and you see that it has a heavy complexity because the same subproblems are being called again and again, clearly you could use a cache to cache the subproblems that you have seen again and not recalculate them, and that is one optimal place or one ideal place to use dynamic programming. And another scenario where you might want to use dynamic programming, where it might not be as obvious as the first one, is when you have an optimal substructure. And what I mean by optimal substructure is, like in recursion, we had this recursive substructure wherein if you could solve, some subproblems, you could solve the entire subproblem. Likewise, if you could solve the optimal answer, if you could figure out the optimal answer for some subproblems, and that could lead to the optimal answer for the entire problem, that's a clear case to use dynamic programming. For example, here in the shortest distance, if you could solve the subproblem of the optimal distance from B to F and from C to F, you could trivially solve the optimal distance or the optimal cost from A to F by just doing a 2 plus the minimum of 2 plus 12 or 3 plus 3, right? So this one was trivial as long as you had the B to F and C to F taken care of. So these are the two scenarios where you use dynamic programming. So either when you have a recursive substructure and the same subproblems are being reused, or when you could figure out the optimal substructure. That is, you know that you can find the optimal answer to the entire problem if you know the optimal answer to the subproblems.